A pleasant morning and a warm welcome to you all for the inauguration of AICT Atal Faculty Development Program on Emerging Trends in Applications of Mathematics, sponsored by AICTE Training and Learning Academy. Educate and raise the masses, and thus alone a nation is possible. Quoted by Swami Vivekananda. I am Dr. N.K. Geeta. On behalf of Department of Mathematics, Dayananda Sagar College of Engineering, Bangalore, extend my hearty welcome to all the dignitaries, distinguished representatives from Dayananda Sagar College of Engineering, head of the institution, head of the department, faculty members, and my dear participants to the inaugural function of AICTE Atal FDP program. It's my privilege to host this morning. I take the immense pleasure in inviting the distinguished dignitaries to this 5 days AICTE Atal FDP program. We have amongst us Dr. CPS Prakash Sir, Principal, Dayananda Sagar College of Engineering, Bangalore, Dr. Harish Sahu, Scientist, DRDO, Delhi, Dr. Ram Jiwari, Professor, IIT Roorkee, Dr. Radha Gupta, Professor, Head of the Department, Dayananda Sagar College of Engineering, Bangalore. In a country famous for its rich cultural heritage and a philauthera of religious beliefs, nothing takes shape without holding our hands in prayer. To begin this auspicious day, in the remembrance of the Lord Almighty, I would like to call Ms. Suma Manjunath to render the invocation. No sound, no sound.
Dr. Geeta, I think there is some problem with the voice. I think we can proceed further. Okay. Yeah.
Yeah. Coming together is the beginning, staying together is progress, and working together is success. With this mantra, I wish all the very best to all the participants for the success of their endeavor in this AICT Atal FDP program. Now I request our beloved principal, Dr. CPS Prakash sir, to deliver a few words about the FDP.
Good morning.
Good morning, sir.
Hello. Good morning.
Sir, good morning.
Good morning. A hearty welcome to all the participants for this 1 week ACT Training and Learning Academy sponsored online 1 week faculty development program on emerging trends in application of mathematics. Now, as we proceed to embrace new education policy 2020, it becomes essential for all the faculty in engineering schools to enable ourselves and to keep ourselves updated with the emerging trends so that we should be able to give the students and train them as per the industry expectations. I am hopeful that this 1 week faculty development program will be of immense value to each of the participants. The end of the faculty development program, at the end of the FDP, each one of the participants will have rich value add, and this FDP, I'm sure, will give an opportunity to interact with experts who are going to deliberate on various issues, will provide opportunity to network with fellow counterparts in the days to come. With good networking and mutual interaction, we should be able to deliver the best to the students. I wish the faculty development program all the best and compliment Dr. Radhakrishna and other coordinators for organizing this FDP in online mode. Wish you all the best. Thank you.
Thank you so much, sir.
Dr. Geeta, we can proceed.
Yes, ma'am. Now I request our beloved head of the department to deliver a few words about resource person.
Yeah, a very good morning to all the dignitaries. Our principal, Dr. CPS Prakash from the Anand Sagar College of Engineering. Our speaker of the next two sessions, Dr. Ram Jiwari from IIT Roorkee, and Dr. Harish Sahu from AICT itself, a representative from AICT, and my dear participants. On behalf of DSI management, I would like to thank AICT Training and Learning Center for giving us an opportunity to organize this faculty development program on emerging trends in applications of mathematics. It gives me immense pleasure to introduce today's speaker of first two sessions, Dr. Ram Jiwari, Associate Professor in Indian Institute of Technology, Roorkee, Uttarakhand. Dr. Ram Jiwari has completed his MSc from Kurukshetra University, India. He has done his PhD from Department of Mathematics, IIT Roorkee, and he has pursued his postdoc from Institute of Industrial Mathematics, Federal University de Paraná, Brazil. Dr. Jiwari has his research interest with numerical analysis and computing, computational modeling and simulations of PDEs, differential quadrature methods, wavelets analysis, radial basis functions, finite element methods, and discontinuous Galerkin methods. He has guided 3 PhD students and 4 are pursuing their PhD under him from IIT Roorkee itself. He has also supervised 25 master theses and he has published more than 50 research papers in peer-reviewed national and international journals. Dr. Ram Jiwari has 5 research projects to his credit as principal investigator, of which one is from National Board of Higher Mathematics, another one from Indo-Uzbek International Project, which is a DST project. Third one is from CSIR. Another one is from SERB, and the last one is from FIG IIT Roorkee itself. Dr. Jiwari is also the recipient of many awards. To name a few, it's Haryana Yuva Vigyan Ratna Awards. He got in 2020, DST Haryana government. Then DAAD Bilateral Award from Germany. He was also a postdoc fellow at Institute of Industrial Mathematics, Federal University de Paraná, Brazil. And also he got a fellowship from FCT, Portugal. He has a very rich teaching and research experience of more than 10 years in various institutes of repute, like Indian Institute of Technology, Roorkee, Thapar University, Patiala, Federal University, Brazil, and B.R. Ambedkar, NIT, Jalandhar. He has organized many workshops and has been invited as guest speakers to many national and international institutes of repute like University of California, Germany, Brazil, Kent State University, USA, Martin Luther University, Germany, TIFR, Bangalore, IIT Bombay, Delhi University, NBHM, Punjab University, Chandigarh, IISc Bangalore, and of course, IIT Roorkee also. Dr. Jiwari is also a reviewer of many refereed journals like Elsevier, Ville Publications, Springer, and Emerald. We have a huge profile with us for Dr. Ram Jiwari. Sir, it is my privilege to have you on board with us today. On behalf of ETEL and the management of the Dayanand Sagar Institution, I extend a very hearty welcome to you and request you to take over the dais. Hearty welcome, sir.
Thank you, ma'am. Thank you very much. So first of all, I am very thankful Dr. Radha Gupta and Dr. Geeta, because they invite me to deliver 2 lectures in this workshop, which is emerging trend in application of mathematics. So actually, I'm very happy to accept this invitation so that I can share my experience, research experience, or how to find solution of differential equation in this workshop. And hopeful this will be beneficial for the participant of this workshop. So I'm also thankful the principal of this college to send me invitation and give me the chance to give my experience to the participants. So actually, I will speak on finite difference method for boundary value problem, because differential equation is the most important tool in engineering and science, because this differential equation means many differential equation arises in science and engineering, which are the models of various physical phenomena. So I will explain how to solve differential equation, because it is obvious that we can solve differential equation in ordinary form and partial form in some particular way, but we cannot solve exactly every differential equation by, you can say, exact method or other methods. So finally, we have to come on numerical methods. Okay, so numerical methods, everyone know we used when we cannot find the exact solution of a differential equation, or you can say partial differential equation, because differential equation are what? Actually, these are the modeled of some real phenomena, or you can say physical phenomena of chemical, physical, and you can say biological models. So because we have to see the behavior of these models, uh, what happens after some time. Suppose this time we have some behavior of the phenomena, and you have to check that what will be happen after 10 minutes, or you can say 10 days, or you can say after 1 year. So in that case, we need the solution of this differential equation or partial differential equation. So actually there are many methods available in literature, or you can say.
Excuse me, Ramji Gari sir.
Yeah, ma'am.
Sir, are you sharing the screen?
Yeah, I'm going to say screen. Yeah,
Okay, sir. Okay, sir.
yeah.
Sorry to interrupt.
No problem. So I think you can see now, yeah?
Yeah.
Hello?
Yes, sir. It's visible.
Okay, so actually I'm starting with the solution of differential equation. So this is it is lecture 1. So I think everyone knows differential equation are divided into differential equations. So everyone know this is ODE and PDE. Okay, so ordinary differential equation and what is partial differential equation, I'm not going in detail because everyone know, because all of you are teachers in some college, and what is ODE, what is PDE, that's fine. But we are starting from here. Actually, ODE are two types: initial value problem, and second is boundary value problems. Actually, initial value problems we can solve by some well-known methods. There is a method, RK4 method. RK4 method means there are many methods: Euler method, Euler modified method, RK Runge-Kutta third order method, fourth order method, fifth order method. But all of and the RK4 method is better, all of the methods in Runge-Kutta methods, because its order is 4, and the number of function of evaluation in each step is 4. So that's why people prefer RK4 method to solve the initial value problem. But you cannot solve directly boundary value problem by using RK4 method. So we have to take help from other method also to solve this type of problem. So, but there are various methods except RK4 method to solve the boundary value problems. So I can say just, for example, finite difference method, second finite element method, and finite volume methods, and wavelets methods. And these days, actually, there are differential quadrature method also popular for to solve the boundary value problems, and you can say many more, because there are many methods to solve the boundary value problems, and mostly boundary value problems occurred in our physical problems. So I'm going to explain these methods for the boundary value problem. First, I will explain for ODE, means ordinary differential equation with boundary value problem, and then I will try to explain also partial differential equation. Simple example, suppose heat equation, and this is parabolic partial differential equation. So, and then I will try to implement this method for this method for boundary value problem in MATLAB also. How to apply, because we cannot solve directly every boundary value problem in MATLAB also. For that, you have to apply some method, and then you have to write the code of the method in MATLAB. So first, I will explain how to apply finite difference method for the boundary value problem, and then in the next lecture we will implement the finite difference method in MATLAB, and we will find the solution of boundary value problem. And we will try to also solve the heat equation, means ut equal to uxx. This is simple example of parabolic partial differential equation, and based on this you can extend your work on the nonlinear also, because this is linear partial differential equation, and you can extend the nonlinear also. Just you have to use one or two scheme for solving the nonlinear, except this. If you are solving heat equation direct by finite difference method, that's fine, because this is linear one, so we can apply directly. But if you want to solve nonlinear one, so to tackle the nonlinearity, we have to take help with one more method also, which will be help to linearize the nonlinear term. Okay, so I'm starting with boundary value problem, and mostly second order boundary value problem occurred in means as a model of various problem. So finite difference methods for boundary value problems. So let y double dash plus px y dash plus q of x y equal to rx. This is a second order ordinary differential equations. Its interval is a to b, and some boundary condition. For example, so I'm saying with boundary conditions, say I'm saying alpha naught y naught plus, okay, so don't try to y naught here. So I'm saying y of a plus beta naught y dash of a is equal to, suppose, gamma naught, and alpha 1 y of b plus beta 1 y dash of b is equal to, suppose, gamma 1. This is at x is equal to a, and this is at x is equal to b. So this is general form. I'm not saying this is particular one, because if beta naught is equal to 0, so this become, then the boundary condition become y of a is equal to something, means gamma naught divided by alpha naught. So this is the Dirichlet boundary condition. I think everyone know there are three types of boundary condition: Dirichlet boundary condition, and Newman boundary condition, and third one is sometimes people say mixed boundary condition, or sometimes Robin's boundary condition. So this is Dirichlet boundary condition here, because y of a means solution is defined at a, and if beta 1 is also 0, so we got y of b is equal to gamma 1 divided by alpha 1. So this type of boundary conditions are called Dirichlet boundary condition. If in second case, if alpha naught is equal to alpha 1 is equal to 0, then this become y dash of a is equal to gamma naught divided by beta 0, and y dash of b is equal to gamma 1 divided by beta 1. So this type of boundary conditions are called Newman boundary condition. So, and third one is what? Mixed one. Suppose Dirichlet also there, and Newman also there. So this type of boundary condition is called mixed boundary condition. So that is mixed boundary condition. So how to solve this boundary value problem by using finite difference method? So first of all, what is finite difference method? Finite difference method. Actually, with the help of finite difference method, we approximate the derivatives. Okay, so first of all, suppose this is our domain A to B. This domain is divided into, you can say, n grid point, or sometime you can say n plus 1 grid points, because I have taken here xn is equal to, this is xn is equal to b here, and x0 is equal to x0 here, x0 is equal to a here. So means that x0 is equal to a, xn is equal to b. So we have n plus 1 points. I'm taking n plus 1 points. You can take n also, there is no problem. Means finite difference method gives solution at these nodes only. At these nodes only. We cannot find solution between these nodes, but we can find solution between the nodes also with the help of, you can say, some interpolation you can use, because if solutions are at these points, so with the help of interpolation you can find the solution inside the points also. Okay, so in everyone know, if we have exact solution, suppose we have exact solution something f of x, so we can find solution at every point. But in numerical method, in finite difference method, only just we can find solution at the grid points only. If you want to find except grid points, so you have to use some interpolation. Okay, so finite difference method, how to approximate the derivative. So first thing is first order derivative approximation, means how to approximate the derivative with the help of finite difference method. So suppose we have y dash, we will approximate this at point I. So there are three types of method: forward difference, backward difference, and central difference. And this time there are many more also. So the first one I can say forward difference. Forward difference means this is approximated by y dash is approximated by y of xi plus 1 minus y of xi and divided by h. H is what? H is the step length. H is the step length. You can say x3 minus x2. Yeah, you can say in general form xi plus 1 minus xi. So you can say this is the h. H is the step length between two nodes, you can say. Okay, plus because we are doing approximation of this, so if you want to write it's equal to, so some error will be there, so its error will be of order h. So similarly, this is forward one. Why it is called forward one? Because this is suppose xi point and this is xi plus point. So what we are doing here, the value of y at this point minus value of y at this point. So we are going forward and come back this. So this is the y of xi plus 1 minus y of xi divided by h. So this is forward one. So what is backward one? Backward difference. Backward difference y dash xi is equal to y of xi minus y of xi minus 1 divided by h plus its accuracy is of only first order. So this in this what we are doing here, this is xi minus 1. So what we are doing, we are approximating y dash at this point ith, but we are going back. So that's why it is called backward one. There is one more also, that is central difference. Central difference. In central difference, we approximate first derivative at xi point, y of xi plus 1 minus y of xi minus 1 divided by 2h and plus order of h square. Means that we are approximating at this point. So we are approximating its derivative at this point minus at this point and divide by 2h. Because why it is 2h? Because the this is h and this is also h, so total is 2h. So that's why it is 2h, but its accuracy is better than the forward one and backward one, because it is h square. Accuracy means what? You can say its truncation error is of order h square. If suppose h you are taking 0.1, so its accuracy will be 0.1 whole square. So this will be 0.01. But in forward one and backward one, it is just only 0.1. That's why the central one is the better the forward and backward one. So similarly, we can approximate the second order derivative at xi point. How this approximates? So first one is suppose forward difference method, forward difference. So okay, FDM is, this is not forward. I will write forward difference. So I'll write this one. This will be y of xi minus 2 of y of xi plus 1 and plus y of xi plus 2 and divided by h square, and its accuracy will again order of h. So this is approximation of second order derivative with forward difference. And similarly, it is with the help of backward one. How this will be? Backward difference y double dash xi equal to y of xi minus 2 of y of xi minus 1 and plus y of xi minus 2 and divided by h square plus order of h. And the central difference y double dash at xi become, so y of I plus 1 minus 2 yi and plus yi minus 1 and divided by h square plus order of h square, where because I'm using here yi means what? Y of xi. So it, for simplicity, I have used this y of yi plus 1 in place of y of xi because this is easy to write. Okay, so these are the approximation of second order derivative with respect to central difference, backward difference, and forward difference. So first what we will do, because our differential equation is this, y double dash p of x y dash q of x y is equal to rx. So we will approximate this differential equation, say its name is 1. We can use this one. So approximate 1, boundary value problem 1 at x is equal to xi with the help of finite difference method we have. So this make first I'm writing y double dash of xi plus p of xi y dash of xi plus q of xi y of xi is equal to r of xi. What I have done, I have put x is equal to xi. Then with the help of finite difference, I will write its value because I need the means higher accuracy. So I will use central difference for second order also, and I will use central difference for first order also because I need the better accuracy. So you can apply forward and backward also, but its accuracy will be less than central difference. So its value with the help of central difference is what? Y of I plus 1 minus 2 yi plus yi minus 1 divided by h square. So I'm denoting this p of xi as pi, and its value with respect to central difference will be yi plus 1 minus yi minus 1 and divided by 2h and plus qi. I'm saying this is qi here. Okay, and yi is equal to ri. So simplify this because one is I plus 1, second is I, and third is I minus 1. So I am collecting the coefficient of I plus 1, I, and I minus 1. So simplifying this one, I will go to, and I will take LCM also, take LCM 2h square, and collecting the coefficient of I plus 1, I and I minus 1. So I will go to 2 minus h pi yi minus 1 minus 2 minus h square qi yi and plus 2 plus h pi yi plus 1 is equal to, or you can say is equal to 2 h square and I. So one thing I want to let you know, suppose our boundary condition are Dirichlet type. So I'm assuming here, first case, you can say case 1. Let boundary conditions are Dirichlet type. Dirichlet. So this means what? Y of A is equal to, suppose I'm saying alpha naught. Okay. And Y of B is equal to beta naught. So I'm saying this one. I'm assuming this one. So that was okay. If you want to take this also, there is no problem. You can take this also, no problem. But so for simplicity, I'm just assuming y of a is equal to some constant of y of b. Okay, don't use alpha and beta because I have used already there. So say it is y 0. Say it is y n, because this is our first point. This is x0 or this is xn. So I'm saying y0 and y n. Okay, small n. Okay, so what we have given solution at here and here is already given. So we have to find solution at the x1, at x2, at x3, and so on. This is xn minus 1. So here, so that I will start from 1, 2 up to n minus 1, because when you will put I is equal to 1 here, so you will get solution at here, at here, at here, at here. So because this solution is given already, y0, this is what? This is y of x0, this is y of xn, means solution at this boundary and this boundary is already given from the boundary condition. So I'm not going here. So that's why I will start from 1, 2, and n minus 1. Okay, so when I'm assuming this adds some constant, say it is ai, say it is ai. Let a is equal to 2. Okay, this is a already here. So some more other constant. Say it is a1. Um, say it is ai is equal to 2 minus HPI. Say bi is equal to minus 2 minus h square qi, and ci is equal to 2 plus HPI. I'm saying this one because I is there. That's why I'm saying ai, bi, and ci. So this become, say it is 2, then 2 become ai, and yi minus 1 plus bi, yi plus ci, yi plus 1 is equal to, say it is capital Ri, the right hand side. Okay, and I is running from what? 1, 2, 1, 2 up to n minus 1. So when I will put a is equal to I is equal to 1, I is equal to 1. So this become a1 y0 plus b1 y1 plus c1 y2 is equal to r1. But this is known to us, okay, because this from the boundary condition already we have given. So y0 already we given. So this imply what? b1 y1 plus c1 y2 is equal to r1 minus its value is again y0. So a y0. Say it is suppose I'm saying first. Okay, when I will put I is equal to 2 here, I is equal to 2 here, so this become A2 Y1 plus B1 now B2 Y2 plus C2 Y3 is equal to R2. Say it is 2. Similarly, for I is equal to 3, this become A3 Y2 plus B3 Y3 B3 Y3 and C3 Y4 is equal to I3. So this is, and so on. When I will put n minus 2, I is equal to n minus 2. So this become a n minus 2 y of n minus 3 plus b n minus 2 and n minus 2 plus c n minus 2 y n minus 1 is equal to r n minus 2. Okay, the last is I is equal to n minus 1. So I'm writing how we can convert this system into a matrix so that we can solve this system with the help of some numerical methods. So n minus 1, so this become n minus 1 y n minus 2 plus b n minus 1 y n minus 1 plus c n minus 1 or y n is equal to rn. As you know that, as I told you that this also known to us from the boundary conditions. Okay, so this implies, so what I'm doing here, I'm modifying this equation and that is equal to that one due to boundary condition. And the last one, in the last one also, this is known to us from the boundary. So this become a n minus 1 y n minus 2 plus b n minus 1 y n minus 1 and is equal to rn minus c n minus 1 and yn. It's both values are given to us. And this matrix, how to write, we can write. Because our unknown are what? Our unknowns are y1, y2. Our unknowns are y1, y2 and yn minus 1. So how to write this matrix? See here from the first equation. First is what coefficient is b1 of coefficient of y1. c1 is y2. So here will be b1, c1. In another second one, it will be a2, b2, c2. So it is a2, b2, c2. Similarly, this will be 0, a3, b3 and c3, and all will be 0 here. Okay, similarly in the last 2 1, so this will become and a n minus 2, c n minus 2 here, and this this is b, because in diagonal I will go to b here, so b n minus 2, here will be a n minus 2, but in last one again this will become b n minus 1 and the a n minus 1. Here will be what in the right hand side? The first one is modify 1, because r1 minus a, r1 minus, not this is not a1, this is a1 here, r1 minus a1 y0, r1 minus a1 y0, this is r2, this is r3, this is rn minus 2, and the last one also rn minus c n minus 1 and y. So this is what, this is a tridiagonal system. This is a tridiagonal system. Okay, so this can be solved easily, or you can say this is this type. How this type? You can say it is a, this is a p plus p y is equal to q type system. This is linear system. Linear system. Okay, I think everyone know how to solve a system, linear system. You can apply any numerical method, Gauss elimination. You can say Gauss Seidel also, Gauss Jacobi also. This is your choice. But this is a tridiagonal system. For this, if you will apply Thomas algorithm, that's name is Thomas algorithm. That will be less computationally, less costly computationally. Its cost will be less as compared to Gauss elimination, Gauss Seidel, and other method also. So if you are solving a bigger system, so apply the Thomas algorithm. Thomas algorithm is nothing. It is the simplest version of Gauss elimination for triangle system. Otherwise, you can solve by Gauss elimination also. Enter this matrix in MATLAB, enter the right hand side. Just there is a one command, you can say y is equal to, from here, y is equal to, enter p and the backslash and q. So you will find a solution from here. This is a MATLAB command. So this was a boundary value problem with the help of finite difference method. So this was a simple Dirichlet boundary conditions. I told you that this is case 1, and boundary conditions are Dirichlet type. In another one, in another case, so you can say case 2. In both of the cases, it will be triangle system. So don't worry about this. What will be the new system? Because in some cases, Dirichlet boundary condition occurred. In some cases, Newman boundary conditions occur. So how I will now I will explain how to solve Newman boundary condition problems. So let y dash of a is equal to, say it is y0 again. No, don't say y0 because it is not exactly given. So it is alpha. I'm saying y dash of b is equal to beta here. Means that at the boundary, no solution is given. You have to find solution at boundary also, and it is just derivative are given at these 2 points. Okay, so let y dash and r the Newman boundary condition. So how to apply? The first thing, this will be the same. Means this system will be the same. Okay, there is no change. But in boundary condition, we are Dirichlet. So we will apply again. What are our boundary conditions? Our boundary conditions are in derivative form. So we will apply here the finite difference for approximation of this. Apply central difference for the good accuracy. Central difference at boundary. At boundary means that this is what? This is given y dash of x0 is equal to alpha. So apply central difference. What central difference says? Central difference says y of xi minus y of xi minus 1 or divided by h. So you can see, if you want to see, this is the central difference. Sorry, I plus 1 and I minus 1, sorry, and divided by 2h here. Or you can apply simple one also, forward one, backward one. This is your choice, as you wish, what you want to apply here. Okay, so you can approximate this also, y of x1 minus, I'm not applying central difference, forward I'm applying forward difference. So y of xi, and in place of xi, what we have this point. I am approximating derivative at x0. So this become y of x1 minus y of x0 and divided by h is equal to alpha. So you can say this imply y1, this become y1 minus y0 is equal to alpha h, and so you can say this is one condition. So it is 1. Okay, so similarly from this condition, second condition, y dash at b is equal to, similarly, is equal to beta, or you can say this imply what? Y dash of xn, because b is what? this point is xn, which is equal to b, or this point is a, which is equal to x0. So this you can say this is equal to beta, or you can apply here again the, so I n plus 1 minus yn, and is equal to beta into h. So yeah, this is the another equation, and yn plus 1 minus yn is equal to beta h. Okay, so these are boundary conditions here, and now with the help of this system, this two system, and these two, I can solve the system and find the again p y is equal to q type tridiagonal system. So I will go to this type of system again. Okay, and the same thing I can use the MATLAB to solve the same. Okay, so now I'm giving an example how to solve this type of boundary conditions, boundary value problems. So for example, a simple example I'm taking here, solve the boundary value problem y double dash 2x y dash plus 2y is equal to 5x, and our domain is what I'm saying, suppose say it is 0.5 up to 0.5, and boundary conditions are what, y of 0 is equal to 1, y of 0.5 is equal to 1.5. So this is our boundary value problem. Okay, so again the same thing, what I will do, I will approximate the domain. Our domain is what? Our domain is 0 to 0.5, and this is equal to x0, this is x1, this is x2. Suppose say I'm saying this is xi, xn minus 1, or say this is xn. And here what we have given, I have given solution at this point, and solution at this point. Say you can say this is y0, solution at this point I'm saying y0 this is equal to 1, or say yn is equal to 1.5, this one, second one. Okay, now approximate say it is 1, approximate 1 with for finite difference method, and I will use central one for the better accuracy, central difference. Okay, so y double dash become y double dash of xi is equal to, as I told you, that this become yi plus 1 minus 2yi and plus yi minus 1 divided by h square, and plus its accuracy become h square. So y dash at xi become what? yi plus 1 minus yi minus 1 divided by 2h, its accuracy become order of h. Put these two in 1, so we got, you can say it is 2, put 2 in 1, we get, so yi plus 1 minus 2 yi plus yi minus 1 divided by h square plus 2 of, because this is 2xi, so this become xi, and yi plus 1 minus yi minus 1 divided by 2h, and plus 2 of yi equal to 5 of xi. If simplifying this one, this is cancel out with this, and taking h square LCM, so this become 1 minus h xi y of I minus 1, coefficient of I minus 1 is this, and minus 2 1 minus h square y of I and plus 1 plus h xi yi plus 1 is equal to 5 h square xi. So I again, as I told you, that 1 to n minus 1, because a solution at boundary is already given. So as I told you, this is ai, this is bi, this is ci, you can write. And how to write its matrix, that's fine, because I will solve this equation. For example, if you want to take just some points, this is suppose 0, this is suppose 0.25, don't take 0.5, 0.1, 0.1. Suppose this is, because this is 0.5, you can take 0.1, 0.2, and 0.3, and 0.4. So if you want to find just its solution at 4 internal point, so you can take help also, calculator also. But more than 4, 5, 6 points, you cannot solve this system by calculator. So we have to write its code in MATLAB, and then just you have to increase number of points. What? Here is number of point 1, 2, 3, 4, 5, 6. Here is n is equal to 6 only. So if you have to find solution, n is equal to 12, 21, 31, 51, 100. So in that case, you have to write its code in MATLAB, and we will solve this system in MATLAB. Okay. So after some time, I will explain how to solve this system. Means I will consider this example in MATLAB and explain how to solve this one. Okay. So I'm leaving this here as you can say this is, if you want to say it is AI, this is BI, this is CI, so you can take, otherwise we can take this also as it is in MATLAB. So I'm leaving this example here, because if I will take just 4 points and explain step by step, so it will take more time. But I'm not going in that one. I will solve this system. This is a tridiagonal system. I will solve this in MATLAB after some time. Okay. So this was boundary value problem. How to solve boundary value problem, ordinary differential equation with boundary condition. But it is also important, most of the people who are doing research in partial differential equation, because ODE is just simplest case, and ODE occur in means few areas where second order differential equation, yeah, you can say ordinary differential equation occur with boundary condition in few areas. But mostly people in research solve the partial differential equation, linear and non-linear. So how to solve the non-linear and linear partial differential equation by using finite difference? So I am going to explain that thing. Just a minute. So partial differential equation. So what is a second order general partial differential equation? This is also a question, because most of the partial differential equation means in research occur of second order. Second order means in space second order, and in time it may be sometime first order differences, partial differences in time, and second order in space if it is parabolic type. If it is hyperbolic type, so that will be second order in time and second order in space also. So I am writing the second order PDE let's consider the second order partial differential equation of the form A uxx plus B uxy plus C uyy, and say suppose some some more extra d is equal to 0. So this type of this is journal second order PD. Don't say journal because if you want to write journal form, so it will be of this type. Means d will be the function of x, y, z, ux, ui, and ux and ui, and it is equal to 0. So this is general one. So this type of partial differential equation can be categorized in three forms. Number one, parabolic. Second one, elliptic. And third one is hyperbolic. Okay, so what is the condition here for parabolic? This is b square, this b square minus 4ac is equal to 0. So this will become parabolic. B square minus 4ac should less than 0. So this is elliptic. And b square minus 4ac is greater than 0. So this is the hyperbolic. Okay. So generally we means categorize in three category: parabolic, hyperbolic, and elliptic. Okay, so how to find the solution of this type of problem, parabolic, hyperbolic, and elliptic? So I will try to explain just parabolic one, because most of the problem occurred in this form, parabolic form. And a simple example of this one is what? Heat equation. Heat equation, that is ut is equal to some uxx. This type of is called parabolic. This is in one dimensional because time is not considered as a dimension. Only just x, y, z are considered as dimension here. So you can say variables are two here. As the solution point of view, t is also variable, but in one dimension, this is t is just a variable, but not a dimension. So that's why this is one dimensional. Into the two-dimensional, heat equation become uxx plus uyy, and in 3D this is in two-dimensional, and in 3D this is xx yy plus uzz. So this is in 3 dimension. Okay, so how to solve parabolic partial differential equation using finite difference? Okay, so I will explain after some time. So elliptic is what? Elliptic, simple example, you can say Laplace equation. Laplace equation, that is what? You can say del u is equal to 0, or you can say uxx plus uyy is equal to 0. So this is the Laplace equation, which is the elliptic problem. And third one is what? Hyperbolic problem, wave equation. Ut is equal to some constant k uxx. So this is one dimensional hyperbolic problem, that is wave equation. In 2D, you can say utt is equal to k del uxx. Del u is, sorry, del of u. So u is what? Del is what? Del is again the same thing. Del is equal to del square x square plus del square y square. This is operator. So this is in 2D. If you will use this operator in 3D, so it will be in 3-dimensional. So now, how to find solution of parabolic problem? Yeah, you can say hyperbolic problem, yeah, elliptic problem in with the help of finite difference. So I'm going to explain that thing. So finite difference operators, as you know that how to approximate the first order derivative, you know how to second order derivative, you know how to explain third order derivative, and so on. Okay, so first of all, so I'm taking an example, method, finite difference method for parabolic PDE Okay, so I'm considering the simple example heat equation. So consider the heat equation. Ut is equal to Uxx, and its domain I'm saying suppose 0 to L. Okay, and T is obvious greater than 0. So we need three conditions here to find its solution numerically. Because or you find if you want to find its particular solution, so we need three conditions. What condition? One is at t is equal to 0. Second one at x is equal to 0. And third one is at x is equal to capital L, because these are the boundary of the domain 0 and L. So without these conditions, we cannot solve this heat equation numerically. And if you want to find particular solution by some exact method, so these three conditions are necessary. Okay, so I'm saying that suppose u of at x0 is equal to, say it is f of x. U of 0t is equal to, say it is u0, and u of at L t is equal to, say ul. Okay, means that solution at this point and solution at this point is, this is u0 and this is ul here. Okay, so these are the boundary conditions, or this is the what? This is initial condition. This is initial condition. So finally, this problem is called initial boundary value problem. If initial condition is given and boundary conditions are given, so this is known as initial boundary value problem. Okay, so how to solve this thing? So first of all, what I will do, I will discretize the domain. Again, the same thing. This is, suppose this is x0, this is x1, suppose this is xi, and this is xn here, xn minus 1. So I is running from 0, 1, 2 up to n. So total points are what? N plus 1 points are here. Okay, so now this is the discretization of the domain into n plus 1 points. Or you can say, I'm saying that delta x, this step length, delta x is what? Delta x is step length, you can say xi minus 1. This is the step length. Okay, and with the help of, you can write in xi in general form also. How to write xi? Delta x into x x0 x0 plus delta x I. For example, I'm saying I is equal to 0, 1, and n up to n minus 1. If you add here, so don't add this here. Okay, I have to add here this x0. Yeah. So when we will put I is equal to 0, so this becomes 0. So x0 is equal to x0. X1 will be what? X0 plus delta x. X2 will x0 plus 2 delta x, and so on. So this is general way how to write this in. We can, because this will help to write its code also. Second thing, our domain is what? This is our domain, but time is also variable, t is also variable. So I'm saying let delta t is the step length in time direction. Okay, in time direction. So means that you can write tj, because here I have used I variable, I am using here j variable. Tj is equal to j into delta t. Okay, so j is running from 0, 1, 2 up to n so on. So I'm not saying it is what is the final here. If our capital T is final time, capital T is final time, then that's fine. So I can say suppose this is m here and capital T is equal to m delta t. This is the final. If capital T is the final time where you want to find solution here. So when you can say, so what our 0 is equal to T0, T1 is equal to delta t, T2 is equal to 2 delta t, and so on. So this is in time direction. Okay. So now just 2 minutes. Just a minute. Okay. So now approximate this derivative and this derivative with the help of finite difference method. Okay. So as you know that ut means what? Ut is function of x and t here. So I will approximate. There are three schemes here. There are the three schemes. Number one, explicit scheme, or you can say method also, explicit method. Second one, implicit. Third one, Crank-Nicolson method. Crank-Nicolson method. So people say it is CN method. CN method also. Okay. So actually, these are three well-known methods for the parabolic PDE: explicit, implicit, and Crank-Nicolson. Okay, so in this method, we approximate the PD at the point xi tj. Here, we approximate the PD at xi tj plus 1. And in this method, we will take the average of this point xi tj and average of these two xi and tj plus 1. This one. So this is the average of both of them. So I will explain one by one. So first one is explicit method. In explicit method, approximate one, that is in boundary. This is say it is one. Approximate one. Yeah, you can say heat equation at xi tj. We have ut at xi tj is equal to uxx xi and tj. Okay, so as you know, this is first order derivative, this is second order derivative, this is in time, this
Ramjivari sir. Sir, we are not able to hear you, sir.
So allow me to share my screen.
Yes, sir.
Okay, yes, sir.
You can share the screen.
Yeah, okay. So unknown is j plus 1, means dot j plus 1. So because as you know that I have to find unknown only. So take unknown one side and known another side. So only this term is unknown. All other terms are known here. So simplifying this, I'm saying this is u I j plus 1 is equal to take delta t multiply that side, and this will become u I j plus u and this is delta t upon delta x square. Inside is I plus 1 j 2 ui j plus ui minus 1 and j. Okay, so neglecting these terms because these are the accuracy. So simplifying this one, say it is r. I'm saying this term is equal to r here. This is r here. So this become I j r u I plus 1 j minus 2 ui j plus ui minus 1 and j. Okay, so and now because this is also uij, this is also uij, so make them together. So this become, and r multiply inside r ui minus 1 j plus 1, this is 1 and minus 2 here 2r uij and plus r ui plus 1 and j. So finally we have this system. Okay, here j is equal to what? J is equal to 0, 1, 2 and so on. So when you will say j is equal to 4, j is equal to 0. So this become what? ui 1 is equal to r u I minus 1 0 1 minus 2r ui 0 plus r ui plus 1 and 0. So this and this all are known from initial condition. Okay, so if you will put everything here, obvious that I is running from 1, 2 and n minus 1. So all are known, so you will get this one. Means that solution, suppose this is u0 is given at delta t is equal to 0 here. So you will find solution at delta t, this one. This is what? This is the ui1 solution at here. Similarly, when you will put j is equal to 1, so you will say ui2 is equal to r ui minus 1 1 plus 1 minus 2r u of I1 and plus r ui plus 1 and 1. So this one, this ui u1 ui plus 1 1 ui minus 1 1, this comes from the previous step, so we will find solution at ui2 at this step with the help of previous one. So this is the explicit scheme. Obvious that why it is called explicit, because this is unknown and this is known here. So if you write y is equal to affect this function, so this is called explicit function. So that's why it is called explicit form. So this is also easy. Sometime its name is also SCMI method also. Its name, sometimes people say Schmidt method also. Okay, so this is explicit scheme. Now the implicit scheme. Implicit scheme. As I told you that approximate PD at the point xi tj plus 1 is equal to at this point xi tj plus 1. Okay, and again apply the finite difference method for this also. So apply here. So this means what? This will become u I j plus 1 minus just a minute. Is this I will apply, this is backward one. Apply here backward and apply here central difference. So if I will backward here, so this is I and j divided by delta t. This is equal to central difference. Apply again central difference here. U I plus 1 j plus 1 minus 2 UI j plus 1 plus UI minus 1 and j plus 1 divided by h square again. So I'm neglecting the order of delta t and order of delta t square. Okay, so simplifying this one, so no delta, this is the delta x square. So this imply j, as I told you that j plus 1 j plus 1 j plus 1 j plus 1 is unknown here. So I will take this side. So this become and multiply that side. So this become ui j plus 1 minus ui j is equal to delta t upon delta x square, and this term here. So again I am saying this is, suppose say it is r. Okay, and simplifying, yeah, you can say collecting the coefficient of ij plus 1 I plus 1 j plus 1 and I minus 1 j plus 1. So this become, using this r and take in the left hand sides because these are unknown. So this become minus r ui minus 1 j plus 1 plus 1 plus 2r uij and minus r ui plus 1 j plus 1 is equal to ui j only, because this term will go, this is only one term is known, all other terms are unknown. So this is our system of linear equations. Obvious that this will give a tridiagonal system here, because we have three things: I minus 1, I, or I plus 1. So if I want to write it's this, so this will be what? This will be tridiagonal system here. So I is what? I is running from 1, 2, and so on. And this is depend upon also what n minus 1, suppose I'm saying n minus 1. Dirichlet boundary conditions are given or Newman boundary conditions are given, because when you will put I is equal to 1 here, so this will give u0 j plus 1. Okay, so just a minute, I'm what I'm assuming here first before explaining this thing. Let U, capital U, I is equal to UI. I am assuming this one. Okay, so that this become easy little well to explain its matrix form. No, don't. Minus R UI minus 1 plus 1 minus 2, 1 plus 2R UI and minus R UI plus 1 is equal to, say it is same, no problem, because this is okay, sorry, plus 1 here. Yeah, because here is J plus 1, here is also J plus 1, because this is J plus 1. Yeah, and this is, leave it, it is same, it is no problem, UI and J. So now when you will put I is equal to 1, 2 and so on, for I is equal to 1, this become minus R U0 plus 1 minus 1 plus 2R U1 minus R U2 is equal to, say it is, I'm saying, suppose say it is Ri, I'm saying it is Ri. So this become R1. Again, when I is equal to 2, so this become minus R U1 plus 1 minus 1 plus 2R U2 minus R U3 is equal to R2. Minus R U2 plus 1 plus 2R U3 minus R U4 is equal to R3. And last two lines, suppose I is equal to n minus 2 and I is equal to n minus 1. So I will go to minus R U n minus 3 plus 1 plus 2R n minus 2 or minus R U n minus 1 is equal to R n minus 2. And similarly, you can say n minus 1 minus R U n minus 2 plus 1 minus 2R U n minus 1 minus R U n is equal to R n minus 1. So you can see that if Dirichlet boundary conditions are given, if Dirichlet boundary conditions are given, so in that case, this thing and this thing be known here, and our unknown will be U1, U2, U3, UN minus 2 or UN minus 1. If the Newman boundary conditions are given, so this will be known. This will also unknown, U0 and UN. So in that case, system will become a little bit changed. Otherwise, suppose boundary conditions are given, Dirichlet type. So in that case, this will become, because unknown are what? U1, U2, U3, and U n minus 1. And right hand side is what? R1, R2, and Rn minus 1. But this R1 will be modified here, this into this, because R is known, U0 is known, this will go that side, like R1 minus plus R U0. Okay, so similarly here also, this will become R UN. Understand? But here will be what? Here will be 1 plus 2R, 1 plus 2R, 1 plus 2R, and 1 plus 2R. This will be diagonal element. And upper diagonal will be, because both are R and minus R, both are minus R. So it will be minus R, minus R, minus R, and minus R, 1 plus 2R, minus R, minus R, minus R. So this is the tridiagonal system for Dirichlet boundary condition. If Newman boundary condition are given, what? U0 and UN will add here, but this system will be changed because first element will be minus R, and then it will be this and this. So you have to take care of that. So this is tridiagonal system, but you can see that capital U is what? Capital U I is equal to U I J plus 1. This system you can write in this form. Suppose this is capital A, this is capital A, and this is n plus 1 you can write here. No, sorry, J plus 1 you can write. J plus 1, and it is equal to, suppose this is right hand side, this is say upon R. For J is equal to 0, 1, 2, you have to solve. Means when I will put J is equal to 0, so this is A U1 is equal to R. Okay, so in that case, you will just find U1, means solution at first step here. Then you will put J is equal to 2, J is equal to 1. So you will see U2 is equal to R. Don't say it is R1 because this will change, right hand side also change. Say suppose this is this is okay. I'm saying here something J, you can say this is R0, this is R1, because this R1 R2 is different from this one. This is a vector here, R0 R1, this is a vector here containing all the elements. So this U2 is solution at next step here, and so on, and so on. So this was a implicit method, and now I think according to schedule of the workshop, this is break time. So we can take 5 to 10 minutes break, and after 11:40 we will start again. Okay, so you can take a break. Yeah, hello, madam.
Yeah, thank you, sir.
Okay, so I will start 11:40.
Yes. Sir. Okay, sir. Thank you, sir.